Does my theory match practice? Is our dimensioning tool working correctly for other frequency ranges? I'm very curious to see what will come out of the reflection measurement on my self-dimensioned antenna. I showed you on the channel how to design and build an interesting loop antenna. I will link you the previous videos on the top right. We already built the antenna for 866 MHz and tested them with LoRa radio technology. We have gained already a lot of knowledge about the properties of this antenna principle in the previous videos. And we at Electronics Unmessed have developed an antenna dimensioning tool that you can download and use for your own purpose. By the way, there is also a video that explains the tool. As a next step, we have dimensioned and set up an antenna for the 2.4 GHz frequency band. There's even a downloadable template for it. Of course, all steps of the dimensioning and the building process of the antenna are documented in videos, which I link in the top right hand corner for you. So, until now it was all just theory, Excel, a DIY guide and paper. Now we want to know if this actually works the way we predicted. You don't miss new videos if you subscribe to the channel. So, there we have the antenna that we made in the last episode. I recommended you to leave the ends of the copper wire longer than necessary. We will now adjust the length of our transformer circuit. To do this, we still have to get the inner piece of wire exactly to the right size. The entire waveguide should be exactly a quarter wavelength. The best way to do this is in two steps. We take measurements in between before we cut off the next piece. It wouldn't be nice if we had to solder a piece of wire back on afterwards. Now I have trimmed the inner piece of wire to the correct length, and as you can see, it all lines up quite nicely with the template now. I also soldered the connection to the inner conductor of our SMA connector after seeing that the feed is actually in the right place. Okay, so far we have done everything to build exactly the loop antenna that we previously calculated with our tool. Now it's getting really exciting, because now it will be shown whether everything I've told you so far is true. We know that high frequency technology sometimes still hides secrets from us that only become apparent during the measurement. We measure the antenna with a so-called nano VNA. This is a small but powerful network analyzer that even a hobbyist can afford. Our hardworking assistant with the Electronics Unmessed t-shirt is currently making the final preparations. The little VNA device is connected to a PC on which we are running the application that we use for the measurement. The application is available for Windows, Linux and macOS, and it's all for free. The device you can grab for less than $100. Here we have the application's user interface, which already looks quite professional. Here we get the measured impedance presented in the Smith chart. I adjusted the Cartesian plot on the right so that we can read the return loss and the VSWR versus frequency. The small device also has an LCD display, which could also be used for this. But I prefer the application because I can use it to save calibrations, for example, and also document the results immediately. Let's go back to the time before we connected the antenna. I call up a calibration for the frequency range 800 to 2800 MHz, which I have carried out earlier. This saves us now the calibration procedure, which takes at least 10 minutes. An SMA open circuit, an SMA short circuit, and a 50 ohms SMA termination are screwed onto the measurement input and measured one after the other. The procedure is tedious and it is therefore worth saving the calibration for different frequency ranges. Right now we are seeing an almost perfect open circuit. The impedance is infinite in the Smith chart and the return loss is 0 on the Cartesian plot because practically 100% of the power is reflected. This is because at this point in time the input of the device is still open. In the next moment, our diligent assistant connects the antenna by screwing the SMA connector tight. That's why we see a pretty shaky signal for a moment. As soon as there is a good contact with the measurement object, we get a clean display of the measurement. We set one of the two frequency markers to 2400 MHz. On the right, we immediately see a return loss of 12 dB and a VSWR of 1.6 at this frequency. This fits quite well with our calculations. Obviously, we hit the center frequency very well. Okay, it's not the best antenna match in the world, but we could certainly improve it by making very small changes to the geometry. In the Smith chart, we see a similar course of the impedance as in the simulation with NEC. However, the course seems to be twisted somehow. And there is a reason for this. You will understand it in a minute. With NEC we had simulated the impedance exactly at the feed point. However, when measuring, we have a small piece of our coax connection between the antenna and our VNA. In the Smith chart, it is this small piece of coaxial connection that causes the twist that we see. Now comes a really cool feature. We can use our software to calculate out this piece of coaxial connection. We do this via the line delay, which we can choose here on the left. If you set a delay of 141 picoseconds, then the measurement appears very similar to our simulation. That's great, isn't it? I need to mention that the frequency ranges do not match exactly. The simulation goes from 1800 to 3200 MHz. The measurement goes from 800 to 2800 MHz. Of course, you have to take this into account when comparing the two impedance curves. And as I said, the impedance match in reality is not quite as good as in the simulation. But with some fine-tuning, it could certainly be improved even further. The Nano VNA has a lot more features. For example, the device could also measure the transmission characteristic of a high-frequency filter and much more. I only use the features here that are interesting for our antenna impedance measurements. The summary and the insights. The exciting question has been answered. The antenna that we calculated shows the characteristics that we wanted to have. Our dimensioning tool actually seems to be working. At least we have now proven that for 866 MHz and 2400 MHz. By the way, now would be a good time to subscribe the channel and don't forget to like the video. Now stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.